All right, so let's talk about how we form a solution and what's going on in the molecular level. So the first thing we're going to say is that the formation of a solution is a spontaneous process. So what does spontaneous process mean? Well, a spontaneous process is one that happens without outside intervention. So it's something that's going to happen on its own, and you don't have to kind of insert extra energy into it. So the example I like to use here we have a hill, and if we place a ball on the hill, which way is it going to roll? It is going to roll down the hill, right? So going down the hill is a spontaneous process. The ball by itself will not roll up the hill. So that would be a non-spontaneous process. So let's take a look at what determines whether a process is going to be spontaneous. So there are two main things that favor spontaneity. So the first main thing that favors spontaneity is a decrease in internal energy. So if we have a decrease in internal energy, that means we're releasing energy. And so what that means is we have an exothermic process. So exothermic processes are more likely to be spontaneous than an endothermic process. And then the second and kind of more complicated one is an increase in the dispersion of matter / energy. And so what this means is that the more dispersed, the more spread out stuff is, the more likely it is to be spontaneous. So if we have an increase in disorder, that's favoring spontaneity. If we have an increase in kind of randomness, we have a favorable process for spontaneity. And what the real word for this is entropy, right? An increase in entropy is a spontaneous process. So we'll touch on entropy when we get to thermodynamics. For now, you just need to know that an increase in randomness causes is more likely to be a spontaneous process. So for example here, we have on one side some gas molecules of neon, and then on the other side some gas molecules of argon. And then we're going to open this separation, right? So there's this thing keeping them from mixing. We're going to go ahead and open that and check out what happens. So when we open that separator, what's going to happen is that the two gases are going to mix and form a homogeneous solution or homogeneous solution. So they're going to be dispersed evenly. And so this is something that's known as an ideal solution. And in an ideal solution, it's a solution formed with no energy change, right? So the picture on the left and the picture on the right have the same amount of energy. And so if they have the same amount of energy, why did they mix? Well, you can see the one on the right is more dispersed or more random. And so why did they mix? It's to increase entropy. And so for now, we're just going to use entropy as a little, kind of buzzword, but later on, we'll learn a lot more about it. Another probably more applicable example is what if we have kind of this hot block over here on the left side, and then we have this kind of cold block over here on the right side. And we're going to say that the hot one is 100 degrees Celsius, and then the cold one is at 0 degrees Celsius. And we're going to say it's the same material and the same amount of stuff. So what's going to happen when we combine these two? Well, the energy is going to disperse as much as it can. And so it's going to go until the two are at the same temperature, right? So they're going to end up both being at 50 degrees Celsius. And again, there's no change in energy here. The stuff on the left and the stuff on the right has the same amount of energy. So why did it happen? To cause an increase in entropy, right? The dispersion of energy. And so this explains why food will go to room temperature if you leave it out, right? If you leave a hot pizza on your counter, it's going to go to room temperature. If you leave a frozen pizza on your counter, it's going to go to room temperature. So there's just a look at some ideal solutions. So there's no net change in energy. However, most of the time, we do not have an ideal solution. And so in order to take a look at this further, we're going to have to think about the intermolecular forces involved.